Morning, good afternoon, wherever you may be in your day. Thank you as always for choosing to make general chemistry part of your day. I think I have a pretty straightforward calculation to perform here, but we're going to look at any Lewis dot structure and be able to determine the formal charge of each individual atom. So you notice where I've been drawing little negatives with circles and things like that next to atoms. Those are formal charges without actually formally talking about it. See what I did there? Not the best in the business for nothing, folks. Okay, formal charge is equal to the number of valence electrons predicted from the periodic table, or what we should start with in our picture where we're putting the dots around, so we got 6 around oxygen, minus however many electrons it ends up with in the picture. So if it gains electrons, it's got to gain that negative. If it loses electrons, it's going to, obtain a positive charge. So what do I mean by that? Well, the first part's easy. Go to the periodic table. So if I go to the periodic table for hydrogen, it's supposed to have 1 valence electron. Oxygen should have 6. Chlorine should have 7. So the first half of this calculation is fairly trivial. All you have to do is figure out how many valence electrons there are. Second part's where the trick comes in. We want to look at how many electrons are attached, except before, if we're trying to determine an octet, we would count everything touching it. Here, we're going to take each of the bonds and assume that they're truly shared, and we're going to split them. So we're going to kind of, if you want to imagine, each bond only counts as 1 electron now. So we're going to split these up. So now if I'm looking at hydrogen at the top, it gets 1 electron per bond, so that's just going to be 1, and our formal charge is 0. That's what we want. We want balance. We want, ideally, there to be no charge or as little charge as possible throughout the molecule. That's going to give you your best picture. So if we look at oxygen A, we have 1, 2, 3, 4, 5, 6 dots, plus the 1 bond gives me 7. This has a formal charge of -1. And this is the same picture as here and the same picture as here. So I don't need to recalculate those. If I look at oxygen B, 1, 2, 3, 4, 5, 6, remember bonds count 1, and this has a formal charge of 0. So this is good. That's what we want. Usually you wouldn't label as 0. So you would just leave those blank there. And this chlorine in the middle, we only have 1, 2, 3, 4 electrons around it, which is +3. That typically is not something you would see in a molecule. The other point here is all of the charges need to add up to the total of the molecule. So we have 0, 0, +3, -1, -1, -1. That all adds up to 0, which is what we should have here, right? No charge. So you can check yourself that way as well. So that's how you would do formal charge calculations. Now you might say, well, is there a better way of drawing the structure? And the answer, of course, is yes, but we have to violate the octet rule. So some people don't like to do this because if you look at chlorine here, you have 14 electrons around. Chlorine we can do that with. It's in the 3rd row, which means it has S, P, and D subshells to fill. So it can go up to 18 electrons. So this is totally fine. It's allowable. We're just going into the d orbitals to do so. And let's go back to how I drew Lewis dot structures a video or 2 ago. So if we were to connect dots, you would get a picture that looks like this over here. And this is a better picture. It violates the octet rule, but it's a better picture. Why is it a better picture? It's a better picture because of formal charge. Now if we do the same thing with our electron counting, hydrogen still has 1, no charge. Oxygen A, 1, 2, 3, 4, 5, 6, has dropped from -1 down to 0. Oxygen B still looks exactly the same. And our chlorine in the middle now has 1, 2, 3, 4, 5, 6, 7 bonds attached to it. And it also has a formal charge of 0. So this is a balanced picture. This is a much better Lewis dot structure. So that's one of the main things we do with formal charge, is to determine why one picture is better than another. The other way we'll use that is if you were talking more organic chemistry into reactivity. Where is your electron density the largest, the smallest? Where's the positive and negative end, forces of attraction, things like that. All right, so let's do something like that where we're given 2 pictures and we want to determine which picture is better. Neither one fits our rules. And a matter of fact, if I were to tell you to just do this the way I taught you, we're going to run into a lot of trouble. So let me show you what that looks like. We got 5, 5, and 6. Let's connect dots, dot, dot, dot. Uh-oh. Ruh-roh. Because what's the problem here? Problem is what? We only have 6 electrons around nitrogen. That's a no-no. have these two openings right here. So that's a bit of a problem. So how would you deal with something like this with the way I taught you? And there aren't too many examples like this, but there are some odd molecules. So what you need to do, and this is going to seem odd, is you need to kind of push these two together. And then with this opening, this is going to go here. So you might predict this is a better picture, although you can see that we're doing a little bit of just pushing around electrons and hoping we end up with a picture that's okay at the end. So that's, if you get in one of these trouble spots and you got more openings and you can't get the electrons, push them together, push the lone ones together, and then do kind of both electrons in a bond for one instead of sharing. If you're trying to split this and do two, that's going to take 10 electrons around nitrogen. It's a no-no. So this is a hard one. This is very tricky to do. So let's just say you realize nitrogen's going to have 4 bonds, so maybe it's 3 and 1, or 2 and 2, or 3 and 1 the other way. How do we figure out which picture is better? And let me throw that last one up here, because why not? It's not the better picture, but who knows? Let's just say we throw all the possibilities out there. All right. We would do a formal charge argument. Nitrogen is always going to be 5 minus, oxygen is going to be 6 minus. Again, that just comes straight from the periodic table. So in this case, nitrogen has 1, 2, 3, 4, 5. 5 minus 5, that's a 0, that's good. This nitrogen's 1, 2, 3, 4. 5 minus 4 is positive 1, and this has to add up to 0, so the oxygen is going to be negative to balance it, but let's go through. 1, 2, 3, 4, 5, 6, 7. 6 minus 7 gives me minus. Okay. Not great. Not all zeros. Let's see. Next one, we have 7 on nitrogen. 5 minus 7 is negative 2. Oh boy, that's not good. This is still positive, and this is also, and this is 5, and this is also positive. So this is bad. This is not a good picture. And if we go to this last one down here, we got 1, 2, 3, 4, 5, 6. 5 minus 6 is minus 1. Positive 1. And then this would be a 6, so 6 minus 6 would be 0. So my question is, what's a better picture? Putting the negative on oxygen or the negative on nitrogen? And again, remember, this means oxygen wins the electron battle. This means nitrogen wins the electron battle. Who is actually going to win an electron battle between nitrogen and oxygen? And if you're saying, well, this is electronegativity, and we got to go to the periodic table and see which one's closest to fluorine, you're absolutely right. Oxygen is closer to fluorine, has a greater electronegativity, should get the negative charge, and this is the best picture, and this picture is out. So this is how we use formal charge. I hope you enjoyed this. Continue to be awesome. Continue to work your homework problems. Hang in there. We're getting towards the end of the semester, and have a fantabulous day.